Good morning, everyone. So today we are going to discuss about paging. So paging is a concept in operating system which is used for reducing the access time by the CPU for accessing data from the main memory. Okay. So before we go into the concept of paging, we must be knowing what is fragmentation. Okay. So at first we'll be having a small introduction about fragmentation and uh, paging is a solution to the problem of external fragmentation. Okay, so at first, before going to paging, we must be knowing what is fragmentation and what are the types of fragmentation, and specifically what is external fragmentation. Okay, so let us say we have a main memory. So this is the primary storage. This is a main memory, and in this main memory or RAM, there are different small slots or the partitions which can hold the minimum unit of data. Okay, so let us say this is our RAM and we have already partitioned it into n sections, and each partition is having the same size. That is, if this partition can hold a data of 1 KB, this will also hold a data of 1 KB, and so on. All partitions will be holding a data of 1 KB. Okay, so all these partitions are equal in size, and what happens is whenever there is a process to be executed or a program to be executed, the program and execution is called process. Let's say we have a program called P0 in our secondary storage. Okay, so before execution, we all know the program must be brought or loaded into the primary storage, that is RAM, and from RAM only the CPU can access, right? Now let's say we have a program P0, and P0 has no, let's say this is the program and P0 has certain instructions in that, and it requires about 3 KB of storage in the primary memory. Okay, now what happens is there are two types this data can be allocated into the RAM. That is, one is contiguous allocation and one is non-contiguous allocation. Okay, now contiguous allocation is very simple. If this 3 KB of data can be stored sequentially, let's say 1 KB here, 1 KB here and 1 KB here, if it can be stored sequentially in these three slots or in these three slots, that is, there should not be any gap or any vacant slot in between. If that is the case, it is called contiguous allocation. That is, the allocation will be continuous. Okay, in case of non-continuous allocation, what happens is that sometimes uh, let's say we have at present we have these two slots being processed by some other process P1, and these two slots being processed by some other process P2, and these two slots are being processed by P3. Okay, now let's say what happens if P2 process gets terminated before P0 requires the RAM. Okay, this is the scenario. If P2 gets terminated before P0 requires the RAM, then what happens is these two slots are vacant, right? And now all these rest all are vacant. Now this is the scenario. These two slots are occupied by P1 and these two slots are occupied by P3. Now if P0 has to run, what the CPU does is it allocates these two slots for 2 KB data, then remaining 1 KB data will be allocated here. Okay, so this is not continuous. Okay, this is non-continuous scenario where the data is not continuous. Now 1 KB is stored here, 1 KB is stored here, then these two slots are not utilized by P0, it has been already provided to P3, then this slot will be used by P0. So whenever such scenario occurs, that is, there is no continuous allocation of memory slot in the RAM for a particular process, it is called non-contiguous allocation. Okay, so this continuous and non-continuous allocation is implemented with the help of these smaller sections or slot of memory, which is usually called frame. Okay, This is usually called frame. Now frame is the smallest slot or smallest portion of or smallest memory unit inside a RAM, which can have a minimum amount of data from the secondary storage and can be stored in the primary storage. Okay, so now we are going to discuss in paging concept, we are going to discuss only about non-contiguous memory allocation. Okay, now in non-contiguous, because the fragmentation is taking place, we have two types of fragmentation. Okay, so the first type is internal fragmentation, second is external fragmentation. Okay, now internal fragmentation is something like, now let's say if we have some 2.5 KB of process. Okay, 2.5 KB process. Now this 2.5 KB, 2 KB can be allocated here and here, as we had already discussed. This can occupy 1 KB, this can occupy 1 KB. Now remaining 0.5 KB is remaining. Okay, so this 0.5 KB can be allocated here. Out of this 1 KB, 0.5 KB can be allocated, and 0.5 is vacant, still vacant. So within these frames, when certain portions are vacant and it can be utilized somewhere else. Okay, so such scenario is called internal fragmentation. Okay, inside a frame a certain portion is occupied. Let's say if this is the frame and this portion is occupied and this is still vacant. Okay, inside a frame when certain portion is vacant, such fragmentation cases are called internal fragmentation. What is external fragmentation? What we had discussed here in the non-contiguous allocation, that is as a slot, as a complete slot it is allocated and certain slots are completely not allocated, it is called external fragmentation. Now this slot is not allocated, right? This and this is allocated and this is allocated, this is not allocated, so here comes a small breakage. Okay, here comes a small breakage in terms of linking of data or linking of slot. So what happens is, let's take a scenario. Let's say we have a table and three chocolates are kept next to each other, so it will be easier for you to just take those chocolates one by one. Now I would say we have three rooms, and in these three rooms somewhere we have hidden our three chocolates, and then you have to find it out. Obviously it will take time, though you may be able to get it, it will take time because you have to search for the chocolate. Similarly here also in the RAM, the CPU has to search for the next data if it is not contiguous. If it is continuous, there is no problem, it can just traverse to the following memory locations. Okay, if the first part is here, then obviously second part will be here, third part will be here, fourth part will be here, it will go on. But what if there is fragmentation or external fragmentation? After each slot being traversed, the CPU has to go and search for the continuing or the next slot throughout the RAM. Okay, so this causes the lack of access speed. Okay, so access speed is reduced because of external fragmentation. Okay, so this access speed can be increased with the help of a similar concept, where what we can do is that we can implement a sort of linked list. Okay, so what we can do, if this is the first slot, we can just provide a link to the next slot at the end of this slot. Okay, and so CPU can jump from this slot to directly this slot, and from here we can provide another link and it can jump to the next slot. So similarly it can be implemented, but it again consumes a lot of time because CPU has to process not only the slot or its instruction or the process, it has to also process the address location of the next slot, so it again consumes time. So paging is a solution for this. So using paging, what we can do is that we can literally memorize the locations within the CPU, and at the time where it is needed, it can directly go to the particular slot. It is similar to memorizing the mathematical table. Okay, table of 2 into 1 to 2 into 2 4. So this, once we memorize, at the beginning for memorizing it will be a bit difficult task, but once we memorize it will be very simple. 2 into 5 10, we can just memorize and say it. Okay, so same concept is used here. So the paging concept implements the task of allocating memories or allocating slot within the RAM by providing the direct address within a table to the CPU. Okay, now how it is implemented? To access the data, what we can do is we can have addressing technique. Okay, so the addressing can be implemented in two ways. Now this addressing is based on CPU to primary storage and CPU to secondary storage. Why secondary storage is there? Till now we have discussed only about primary storage. Why secondary storage is there? Because all the process is at first it is available in the secondary storage only. From there it is loaded onto primary storage and then it is executed, right? So CPU has to know the address of the secondary storage, then it has to know the address of the primary storage, then only it can process. So there are two types of addresses. First one is logical address, second one is the physical address. Logical address always corresponds to the secondary storage. Physical address always corresponds to the RAM or the frame address. Okay, the individual frame address is what we call as physical address. Okay, to memorize it there is a simple technique: physical P, primary storage, right? So primary storage also P. So this with PP, the initial letters, you can easily memorize. The physical letters corresponds to the primary storage. The primary is RAM, we all know that. Okay, so this logical address of the secondary storage is generated by the CPU. Okay, but the physical address of the RAM, it cannot be generated by the CPU. It has to be derived with the help of paging. Okay, so why we require logical addresses? As we had already discussed, it the process is available in the secondary storage. Now what happens is, to transmit data from the secondary storage to the primary storage, we manipulate the secondary storage in the sort of paging. We split the secondary storage or the process individually into certain sections which are called pages. Now page in secondary storage corresponds to the frame in primary storage. Both will be of equal size. If primary storage is of 1 KB per frame, then the page will be of again 1 KB size, okay, in the secondary storage. So the task of CPU has been considerably reduced. It is a simple task now, just to copy and paste it in the RAM. Okay, it doesn't have to split the data. It doesn't need any extra manipulation of data. Okay, it just needs to copy a page and put it in a frame. It is as simple as that. Now once the data is in the RAM, it has to generate the address of that individual frame. Okay, so that is implemented with the help of the paging. Now in paging, what it does is that CPU generates the logical address that is of the secondary storage. Okay, the logical address has two parts. One is the page, that is, if CPU accesses a secondary storage, obviously there will be pages as we had discussed. So this page where the process is present, so that address can be generated by the CPU. It can easily access the secondary storage, so no complications there. So that page address is present here. Now D is the instruction offset. D is the instruction offset. Now what is instruction offset? Let's say if I give you a book and I tell you, please go to the page number 30 and read the second paragraph. So that is very simple for you. You can directly go to page number 30 and read the second paragraph. Similarly, when a process is executed, process is in a static situation, it is called program, right? So when there are so many instructions, if the CPU has to execute the fifth instruction specifically, so this number of this instruction is provided here as an offset. Okay, now this page corresponds to the overall location, and D or the instruction offset corresponds to the individual instruction available inside the page. Okay, so that is as simple as that. So a set of instruction is available in the page, and inside the page we can specifically say please execute third instruction or fourth instruction. Okay, so that is the offset. So first concept that we must be remembering is that, as we had discussed here already, that the page size and the frame size are always equal. That is, if the instruction number 3 is available on a page, it will be again instruction number 3 itself in the frame as well. Okay, only the page address and frame address will be changing, otherwise the offset or the number of instruction or the nth instruction will remain the same. So we can do one thing, we can to translate the address from logical address to the physical address, the instruction offset is copied as such. Okay, only thing that we have to change is the physical address. Okay, so what we do is we take a data structure. This is a data structure. Data structure is simply a table or organized form of data, and this data structure is called page table. Now page table consists of two columns. First one is the page number that corresponds to the secondary storage. Second one is the frame number that corresponds to the primary storage. Okay, so here a mapping is done for each page to frame. Let's say if it is 5th page, then the corresponding frame number, let's say 120th frame. So it is just a dummy data that I am providing. So intention is to tell you that each page number corresponds to a frame number. Okay, so once the frame number is determined through the page table, this frame number is copied here into the frame. Okay, here it was existing, let's say 5th page 10th line of code. Okay, so 10th line of code, here also it will be the same 10th line of code. 5th page corresponds to the 120th frame number. Okay, that is 5th page of this hard disk has been copied to 120th frame of the RAM. That is 5th page of the hard disk has been copied to 120th frame in the RAM. Okay, so this corresponds to 120th frame. In 120th frame we have to execute the 10th instruction. So this is the physical address that we have derived from the logical address. Now this physical address is executed by the CPU. So what happens is here the access time is considerably reduced because we already have a page table that corresponds to the mapping between page and frame. Okay, now the size of the page table depends on the size of the hard disk or the secondary storage. Okay, now it doesn't mean that secondary storage has GB and TB of data, so page table will be also having similar length. No, page table is always corresponding to a process. Okay, so if we have a process P0, it will be having a different page table 1. If there is process P2, it will be having some page table 2. So each time a different process is executed, a new page table is created and the entries are made. Okay, so this length of the page table depends upon the process in the secondary storage. Okay, so this is the basic explanation for the paging. I hope the concept is clear. So that's it for today. See you in the next class. Thanks for joining. Thank you.